In this lesson, we're going to talk about the indefinite integral and net change. So we're going to identify the difference between definite and indefinite integrals, define net change as an integral, and then interpret definite integrals in terms of real-world situations. So the first thing, let's just recap the difference between a definite versus an indefinite integral. So on the left, we have a definite integral. So this is a definite one. And we can tell it's a definite integral because we have bounds, the lower limit and the upper limit. When we evaluate this, our answer is going to equal a number. And we talked about that before. An indefinite integral is this one on the right, and this is indefinite. And the reason it's indefinite is because we do not have any limits, no lower limit, no upper limit. When we go to evaluate this, we are going to end up with our answer being equal to a function. Okay, so definite integral, the answer is a number. An indefinite integral, the answer is a function. So what the indefinite integral is pretty much just the antiderivative. So we talked about that in an earlier lesson. We're just giving it a different name now. So an antiderivative is just an indefinite integral. Here is your table of indefinite integrals. It's exactly the same as our table of antiderivatives. So we have a function and then plus the arbitrary constant plus c. So find the general indefinite integral. So this is the same thing as saying what is the antiderivative. It's just instead of saying the word antiderivative, it has this symbol of the integral with no upper or lower limit. So we can do this one of two ways. We can use our properties of integrals and separate things. So maybe we take the 10 out because it's a coefficient. We have the integral of x to the fourth dx. Minus, I'm going to take out the 2 because it's a constant, and then I have secant squared x dx. From here, I know that the antiderivative of x to the fourth is going to be 1/5 x to the fifth, right? Because I'm going to increase my exponent by 1 and then divide by that number. And then the antiderivative of secant squared, so remember you can work backwards, so we could say that the derivative of what will give us secant squared, and that is tan x. And then we can't forget our plus c at the end. So if I multiply 10 times 1/5, I'm just going to get 2x to the fifth minus 2 tan x plus c. Okay, if you did not want to use the properties and separate everything like I did here, you could just apply the reverse power rule to the 10x to the fourth. So for instance, I'm just going to draw a little arrow here, right? If I have the integral of 10x to the fourth, I can increase the 4 by 1 to get 5 and then divide the 10. So I get 2x to the fifth. So you don't need to break it into this step if you don't want to. You could just work from it this way as well. Okay, so now we're going to look at a definite integral. So this is just kind of like a repeat of what we were doing last class. So remember that there is no reverse quotient rule. So what we want to do is use algebra to kind of simplify this a little bit. So we're going to have the integral from 1 to 9. And if I divide everything by t squared, I'm going to have 2 plus t to the 1/2 minus t to the negative 2 dt. So I'm going to take the antiderivative of what's inside. So that's going to be 2t plus, and then this would be 1/2 plus 1 is going to give me 3/2. So I'm going to divide the one that's in front of this t by 3/2, t to the 3/2. And then this is going to become plus because when I add 1, I get -1, and then I divide by a negative, and it becomes positive, t to the -1. So I'm just going to rewrite this piece here. So when I do 1 divided by 3/2, that is just the same thing as 2/3. So t to the 3/2 plus t to the -1. And then I'm evaluating it from 1 to 9. So what I'm going to do here is plug in 9, and then I'm going to go and plug in 1. So I'll do 2 times 9 plus 2/3, 9 to the 3/2 plus 9 to the -1 minus 2 times 1 plus 2/3, 1 to the 3/2 plus 1 to the -1. Okay, so technically I could leave this as my answer as long as I've plugged in my values. That's good. I do not want to leave it like this one. Okay, that is not fully simplified because we didn't plug anything in. So you can leave it like this without simplifying. If we do simplify this, it ends up as 292 over 9, which is about 32.444. On your web assign for tonight, you will have to put in exact answers, so keep it like that. Normally, you can use decimals and round it. However, just to be safe, keep everything as exact as possible. So now we're just going to move on to net change. So this is something that we've already done. Net change is just the integral of a rate of change. So when we have an integral and we take the antiderivative and plug in the top limit minus the bottom limit, that is going to give us the net change. And a couple of examples of net change. Here's a good example of volume. So V of t is the volume, and you have V prime of t is the rate at which the water is flowing into a certain reservoir. If I take the integral from T1 to T2, what I'm finding is the amount of water in the reservoir between the two times. So that is like the net change of the amount of water. Okay, so a lot of times we talk about it in terms of a particle moving, and we've talked a lot about particle motion with position, velocity, acceleration. So if an object moves along a straight line, then its velocity is v of t, which is s prime. So the integral of the velocity is going to be the position at the different time values and subtracting them. And that is just called your displacement. So the net change of the position is the displacement. So we're just kind of giving things like different names. Okay, we also talked about before total distance traveled. So that would be absolute value of the velocity. So it's still the idea of net change, but in this case, remember that the signs are always going to be positive. So both displacement and distance traveled can be interpreted in terms of area under the velocity curve. Again, just a review. So displacement would be a1 minus a2 plus a3, because a2 is below the x-axis, it's going to be negative. The distance, the total distance traveled, is the absolute value. So even though a2 is negative because it's below the x-axis, we're going to make it positive because we have to include that in the total distance. And then same thing kind of goes for acceleration. So acceleration is the derivative of velocity. So if I take the integral of the acceleration between t1 and t2, then I get the change in velocity. So to just, again, sort of recap something that we've already talked about, there are 3 ways that we can use integrals when we study motion, and it's kind of easy to confuse them. So we just want to be careful. So the first thing is when you have the indefinite integral. So the integral of v of t dt, because there's no values or our limits of integration are not there, this is an indefinite integral. So I'm just going to write that in. And that is going to give you an expression for position at time t. Don't forget that you will have a plus c, which is the value of which can be determined if you know a position value at a particular time. So that plus c is your constant of integration. So when you have an indefinite integral, you're going to have the plus c. Now for number 2, you have an integral, but it goes from t1 to t2. So that is a definite integral. And so the answer will be a number. The number represents the change in position over the time interval. So by the fundamental theorem of calculus, which we talked about last time, since v of t is equal to x prime of t, the integral will yield x of t2 minus x of t1. This is also known as displacement. The answer can be positive or negative, depending upon if the particle lands to the right or left of its original starting position. And then number 3, we have the integral from t1 to t2 of the absolute value of v of t dt, and that is also a definite integral. And we could see that because we have values for our limits of integration. So the answer will be a number. The number represents the total distance traveled by the particle over the time interval. The answer should always be positive. Okay, so these are 3 things that we should already know, but just kind of refreshing it because with net change, this comes into play again. All right, so let's look at a couple of real problems involving this stuff. So if v of t is the velocity of a particle moving along the x-axis at time t, and the position x of t is 5 at time t equals 2, write an integral expression that represents the position of the particle at time t equals 10. So if I want to find the position, so I want to find x of 10, that's what I'm trying to solve for. They give me this initial condition up here, and they said that the position is 5 at t equals 2. So that means x of 2 is equal to 5. So that's where I'm starting from. That's my initial position. So x of 2 plus the integral from 2, because that's where we're starting, to where we're going, which is 10. And this will be v of t dt. Since I know x of 2 is equal to 5, I'm just going to substitute that in. So the position at 10 is going to equal 5 plus the integral from 2 to 10 of v of t dt. And then for part B, write an integral expression that gives the total distance traveled by the particle from time t equals 2 to time t equals 10. So total distance traveled, we're going from 2 to 10. Because it's total distance, we're going to use absolute value of v of t dt. Okay, so here we have a particle moves along a line so that its velocity at time t is this thing. Find the displacement of the particle during the time period 1 to 4. Okay, so now we're going to set this up as an integral, right? Because displacement means I'm going to use the integral of the velocity, not the absolute value, just the velocity. So my interval is between 1 and 4. So here's 1, here's 4, and I'm using my v of t. So I know what that function is. It's t squared minus t minus 6, and I'm going to put dt here. Okay, so what I'm going to do is find the antiderivative of this. So I'm going to use my reverse power rule. So I'm going to get 1/3 t cubed minus 1/2 t squared minus 6t. And I'm evaluating that from 1 to 4. So I'm going to plug in 4 for my t. So again, I could leave my answer technically like this with everything plugged in. Okay, I can't leave that as my answer. I have to make sure that I at least plug in everything that, put this in brackets, minus 1/3, that's 1 cubed, minus 1/2, 1 squared, minus 6 times 1. And then if we solve this correctly, this is going to give me negative 9/2, which is negative 4.5. So remember that displacement can be negative, and that just means that your particle is to the left of where it started. So since it's negative 4.5, my answer would be 4.5, and in this case it's meters, but I'm going to say to the left. All right, so since I know it's negative, I know that it's going to be 4.5 meters to the left. All right, the next 2 problems, we're just going to look at how we can explain what it's asking for. So if b of t is the rate of growth of the number of bacteria in a dish, measured in number of bacteria per hour, what does the integral from 2 to 6 of b of t dt represent? And answer in correct units. So the main idea here is that what's inside the integral is a rate of change, right? It's the rate. So when I take the integral of that, that is going to give me like the number or the amount. So in this case, because I'm going to find the amount at 6 minus the amount at 2. This is actually giving me the change in the number or the amount of bacteria between T equals 2 and T equals 6 hours. Okay, so notice that I'm not using the word rate, right? Rate is what's inside the integral. Once I take the antiderivative and I plug in the values, I'm getting the net change. So I'm getting the change in the amount or the number of bacteria. And I want to make sure that I have the right units for the bacteria and for the time frame. Okay, so let's look at one more like this. So if P of T is the rate of growth of a rabbit population measured in rabbits per year, and there were 100 rabbits in the year 2005, which we're going to count as T equals 0, write an integral expression that represents the rabbit population in 2007. So P of T is the rate of growth. So that's going to be what goes in the integral, but I'm trying to find the number of rabbits, right? How many rabbits there are in 2007. So if T equals 0 is 2005, that means 2007 is going to be T equals 2. So I'm going to find P of 2, which is going to be P of 0, which is what I started with, plus the integral from 0 where I'm starting to 2 where I'm ending of P of T dt. So what I'm trying to do here is take the original amount of rabbits and I'm adding the change in rabbits from 0 to 2 years. So P of 0, we said here is equal to 100 plus the integral from 0 to 2 of P of T dt. And because we don't have an actual P of T function, we're just going to leave that as our answer. Okay, and then last one here, water leaks from a tank at a rate of 2 plus 5T liters per hour, where T is the number of hours after 7 a.m. How much water is lost between 9 and 11 a.m.? So the first thing that we have to think about here is what is the integral that we're using, right? Because it's leaking at a rate of this, right? So that is going to be my rate. That is my value that I'm going to have inside the integral. The interval itself is between 9 and 11, right? But notice it says where T is the number of hours after 7 a.m. So we're not using 9 and 11 as our limits of integration. If it starts at 7 a.m., 7 a.m. is going to be T equals 0. So at 9, this is going to be T equals 2. And at 11, that's going to be T equals 4. So my integral is going to be between 2 and 4 of my rate, which is 2 plus 5T dt. But the key here is that water is leaking from the tank. So if it's leaking, I'm going to have a negative in front. So now I'm going to take the antiderivative. So I'm going to keep this negative in front. And I'm going to get 2t plus 5 halves t squared. And I'm evaluating that from 2 to 4. Okay, so I have that negative on the outside. Put that here. So again, I'm just going to plug in the 4 first. So plus 5 halves 4 squared minus 2 times 2 plus 5 halves times 2 squared. I think I have too many parentheses. Anyway, when we do this, we end up with negative 34. All right, and it's okay, it's a negative because that's how much it's losing. So that means that the tank lost 34 liters of water, right? That's the net change. It's a negative 34. And then it's between 9 and 11 a.m.